Okay, so let me summarize what we were talking about out of 9.1 and 9.2, which, if you recall, is so I would describe it as being about uh, stability or instability of systems of differential equations. Really, this is about 2 by 2 systems. The stuff that we're talking about is applicable to higher, like 3 by 3s and so on. But we're in this class, we're just going to talk about it in the context of 2 by 2 systems. So we have two variables. It could be x and y, or it could be x1 and x2. And we have the derivative of x is written as a function of both of them, and the derivative of y is written as some other function of both of them. We have what we call, and this is new terminology. This is we used partial derivatives for the last example. If you go and look back, I didn't use the word Jacobian, but we have this matrix. It is called the Jacobian. It's the matrix of partial derivatives. So I take this function f and I do the partial with respect to x and y, and then this function g, and do the partial with respect to x and y. So in Calc 3, you would have seen the Jacobian before, but this is maybe a new context in which you're seeing the Jacobian. But it is just this matrix of partial derivatives. So if you recall, a critical point or an equilibrium point is where x prime is 0 and y prime is 0. So in other words, like this is 0 and this is 0. So yeah. And then to determine whether such a point is stable or unstable, what you do is you find the eigenvalues of the Jacobian at that point. So you find the critical point at x naught, y naught. And then, right, this function j, these are partial derivatives. These partial derivatives might still depend on x and y, but you plug in that value of x and y there. So after that, the Jacobian is just a matrix with specific numbers in it. and you find those eigenvalues. If they're all negative or they have negative real parts, then we say it's that the critical point is stable. Also, in that case, it would also be asymptotically stable, meaning that the solution is not just kind of circling around and around the critical point. It's actually moving ever toward that critical point. And as time goes to infinity, we're going to get as close to the critical point as we would ever want to. So in the limit, it really is equal to the critical point in the limit. So that's this case, when all the eigenvalues are negative or at least have negative real parts. If any eigenvalue is positive or has a positive real part, then it is unstable. And then if the real part isn't positive or negative, in other words, if the real part is 0, in other words, if the eigenvalue is pure imaginary, the real part is 0, so it's like 0 plus or minus qi. For this, we're going to say it's inconclusive. There's more that I can say. You do get some information out of this, but I will just say inconclusive. Out loud, I'll say maybe a bit more. What is this? If we were definitely talking about a linear system, this is the case when the solutions are just ellipses circling the critical point. If it were perfectly linear, then these solutions would be ellipses. And those are the types of things that we called stable but not asymptotically stable. It's stable in the sense that it's not moving away from the critical point. It's just sort of circling around and around. But it isn't asymptotically stable in the sense that it's also not getting closer and closer to the critical point. It's just circling around. It's staying roughly the same distance or so. and that's what would happen if you were in this case and it were perfectly linear. But again, we are now talking about things that are almost linear. So if you can imagine like something trying to behave like an ellipse circling around and around the same point, but there's a little bit of error now, which may push the point closer to the, which may push your solution closer to the critical point or farther away from it. And the fact that it might not be perfectly linear, there might be that little bit of error, is what really makes this completely inconclusive. The curve might actually move towards the critical point or away from it. So, yeah, if that happens to us in real life, we'll just say inconclusive as far as we're concerned. Anyway, so it's not that complicated. To find and characterize the critical points, once again, you just set both of these things equal to 0. You find some solution for x and y. You plug that in here, you find the Jacobian at that point, and then you find the eigenvalues of the Jacobian. And whether those eigenvalues have a positive real part or a negative real part, or whatever they have, tells you the answer. It tells you the stability or instability at that point. So let me do another example. It's this one. So the instructions are find critical points and classify them as above. So let's do that. So set both of these equal to 0. So I'm going to find the critical points, set these both equal to 0, and if I want to be smart about this, maybe instead of writing this equals 0, I'll write this equals 8, and I'll write this equals -10, because I can already see what I'm probably going to do, which is just kind of normal stuff for solving a system. Like this is just a linear system of equations. And you know, this is pretty easy, so maybe I shouldn't talk too much about this. I'll just do the first equation minus the second equation. So I'll get -6y equals 18. So y equals -3, and then I put that in. X plus 6 equals 8. X equals 2. Okay, so it would seem that there is only one critical point, 2, -3. So let's characterize that. And yeah, let me grab another piece of paper. We have the Jacobian, and for now let me call this j of xy. So I'm filling it in, so it's this matrix of partial derivatives. So I take this, partial with respect to x would just be 1. Partial with respect to y would be -2. Partial of this with respect to x would be 1. Partial of this with respect to y would be 4. And actually, I called this j of xy. In general, like for completely general functions, when we do these partial derivatives, these entries may be functions of x or y. Currently, we're doing a relatively simple function, so these partial derivatives were already just numbers. Normally, if these were functions of x and y, what I would do now, of course, is I would plug in the specific value of x and y to actually get numbers here. But for me, it's easy, so if I were to plug in 2 and -3, I would just get this. So there's not too much to think about. In any case, what I'm interested in is the eigenvalues of this matrix and whether they have a positive real part or a negative real part. Hopefully they don't have 0 real part, because then I'm inconclusive, but if that's the case, I'll just say I'm inconclusive. So, yeah, we've done this before. This is just finding the eigenvalues of a 2 by 2 matrix. And this is easy because I don't even need the eigenvectors to determine whether this is stable or unstable, just the eigenvalues. So that. So I've got, actually, okay, I don't want to be too lazy and go too fast. So it's like that, and I multiply this out. I've got a lambda squared minus 4 lambda minus lambda, so minus 5 lambda plus 4 plus 2, so maybe I'll write plus 6. And that looks good because that's lambda, lambda minus 2, lambda minus 3. So actually, both of our eigenvalues were positive, but if I look at this summary, even if I had one eigenvalue with a positive real part, I would say it's unstable. But I have 2, so it's, I don't know, it's doubly unstable or something. But that's not a real thing. We just say unstable. Okay, so I'm going to shut this off and then probably record another video with another example.